You know about this. Any more notes coming in for early birds? If so, I gotta have them. Let's get at the stuff for which you will be responsible on exam 1, which is through buffers. So we need to proceed through question 43. If we don't get that far with this talk, I will post the explained solutions to whatever parts of the remaining questions that we don't tackle on the Sakai website. We'll see where we are when we finish our chat. Back to our demonstration from last time. When we mixed the blue solution with the yellow solution to make a yellow solution, and the blue solution with the yellow solution to make a blue solution, and then the blue solution with the yellow solution to make a green solution. Did you recognize why, before we did the demonstration, it was not possible to predict the resulting color? With a blue solution and the indicator HBTB, all you know is that the pH is 8.0 or above. With a yellow solution, all you know is that the pH is 6.0 or lower. Might be 5.0, 2.0, minus 1.0 for 10 molar hydronium ion. So what we discovered when we made the mixtures, given that the first one wound up being yellow, is that the quantity of hydronium ion in the yellow solution exceeded the quantity of hydroxide ion in the blue solution. We don't know by how much, but we know enough to generate a resulting hydronium ion concentration of at least 10 to the minus 6, pH 6.0, result yellow. Blue solution, the hydroxide ion exceeded the hydronium ion concentration. And when we resulted in developing the green color by mixing the blue and yellow solutions, did we have now cause to recognize that the mole amounts of hydronium ion and hydroxide ion which were mixed compared how? How? Equal moles. Because green, shown by HBTB indicators, has a pH on the order of 7.0. That means neutral. That means a water solution for which the hydronium ion and hydroxide ion molarities are one and the same. So for water at room temperature, that's on the order of 1 times 10 to minus 7 moles. Now for question 34, which we also did last time. We took 1 molar acetic acid, treated it with methyl orange indicator. Saw a deep red-pink color. Combine that with an equal volume of deionized water treated with the same indicator, which initially was goldenrod color. And this time, before we made the mix, I said, if you think about this, you can flatly predict the resulting color. Because all we really did was to dilute 1 molar acetic acid to half molar acetic acid. And we've now analyzed, in particular, acetic acid solutions on a number of occasions. The change in hydronium ion concentration on going from 1 molar to half molar acetic acid ain't much. And the indicator color pH data which we have supplied reminds you, you have to produce a rather substantial change in pH before you can get an observable change in color. Well, when you go from 1 molar acetic acid to half molar acetic acid, you don't get that substantial change in pH. So the resulting color was the same as the 1 molar acetic acid, practically speaking. The same red-pink color. With that, we go to question 35, another indicator color. Question 35 is one of my favorite hypothetical indicators. Gator xanthus, which I stipulate shows these colors for these corresponding pHs. Now keep in mind, as by now you should recognize, for an indicator. All we have to do is to supply you the boundary pHs, and then you can fill in the rest. Because when you have the boundary pHs, 0.9 and 2.5 respectively for this indicator, because when you get this thing to a pH of 0.9, it is a distinct yellow. And any lower pH, it's still a distinct yellow. When you get this thing to show a blue color at a pH of 2.5, at any higher pH, all you see is the same blue color. So with these boundary pHs, if you add them up, divide by 2 to get the midway pH, you recognize that at this midway pH, to what extent is the indicator ionized? 50%. That means you have a solution with the indicator HGX, which if it's ionized 50%, contains equal mole quantities of GX minus, which for this indicator is the blue stuff, with HGX, the yellow stuff. Well, we know, because we played with watercolors when we were kids, didn't we? When you mix equal amounts of yellow and blue, then you get green. So at this 50% ionization extent, we recognize that the hydronium ion concentration corresponding to the pH at this 50% ionization extent is equal to Ka for the indicator. That's it. So the pH is 1.7, for which the hydronium ion concentration is 2 times 10 to the minus 2. Bear in mind, you should know this by now, this is 1 sig fig. These are logs. The only significant figure portion of a logarithm are those digits which appear in the mantissa, the digital entries to the right of the decimal point. This is a decimal point locator. It's not measurmentally significant. And for this, for question 35, we've stipulated that we're going to deal with an HQ solution, another hypothetical acid, and presume that HQ is an acid as strong as HGX. That means the Ka values are equal. And now, the second part of the experiment described by question 35. We have an HQ solution. We'd like to know what the numerical value is for the label on the bottle, the M sub I value. To find out, we take this colorless HQ solution and treat it with our indicator HGX and observe a distinct YG color, yellow-green. Well, we see a distinct yellow-green at pH 1.3. In this range, it's more yellow than green. In this range, it's more green than yellow. So we'll take the pH to be 1.3 because of the observation, for which the hydronium ion concentration is 5 times 10 to the minus 2. From this, can we calculate M sub I for HQ? You betcha. Here's the equilibrium constant, which corresponds to Ka for HQ. The Ka value is this. We have a single solute system, HQ. So the x squared over M sub I minus x recipe applies, which means the hydronium ion concentration and Q minus concentrations are equal, both 5 times 10 to the minus 2. And in the denominator, we then have M sub I minus the concentration of derived species, which is Q minus, which for this system is also equal to hydronium ion molarity. There it is. One equation, one unknown, solve it. Done. Question 36. Another hypothetical acid, HC. The only stipulation regarding HC is that it is an acid which is found to be twice as strong as HGX, which means that it's also twice as strong as HQ. That means its Ka value is double that. End of story. Questions 37 and 38. And for some of you, 39 and 40 were done yesterday in discussion class, but everybody at least got through 38. So we'll go to question 39. Now, we're dealing with buffers. We talked about buffers yesterday and how they behave. You've all heard about buffer solutions, I'm sure, before you even got into chemistry class. Did you know that human blood is a very important buffer system? Just like sweat and tears? Important human buffer systems. Even urine. Happy human blood buffers at about pH 7.4. Boundary region 7.2 to 7.6. If you're in there, you're okay. If your blood tests for pH and shows to be less than 7.2, the medical people will state that you have a condition known as acidosis. Blood is too acidic. Above 7.6, alkalosis. Blood is too basic. Now, I've told you, you might try to escape from chemistry, but chemistry will never escape from you. You are a marvelous composition of all sorts of important chemical systems, each of which takes place in guess what solvent? Water. That's why I am so emphatic about this stuff. Water solution chemistry. Question 37 reminds you, forget this recipe when you're dealing with buffers. Forget this recipe when you deal with any solution for which, beside the ionizing solute, you have an additional source of hydronium ion or an additional source of hydroxide ion. Because in any such solution, the conjugate base of the ionizing acid will have a molarity that's not the same as the hydronium ion concentration. For a basic system, the conjugate acid of the ionizing solute base will have a molarity that's not the same as the hydroxide ion concentration. And if it is a buffer solution, and it's an acidic buffer solution, the conjugate base molarity will be much higher than the hydronium ion concentration. If it's a basic buffer system, the conjugate acid molarity will have a much higher, the conjugate acid molarity will be much higher than the hydroxide ion concentration. Question 38 was asking you to consider the production of an ammonium ion buffer before you do anything with pH calculation for such a system. You should stop to ask yourself the question, is this going to be an acidic buffer or a basic buffer? The example discussed in the textbook is an acetic acid acetate ion buffer. Well, I checked the data points which are relevant to this issue, specifically Ka for the acid and Kb for its conjugate base. Ka acetic acid, 1.8 times 10 to minus 5. Kb for acetate ion, conjugate base of acetic acid, is 5.6 times 10 to minus 10. Which tells me acetic acid does a hell of a lot better job behaving as an H plus source than acetate ion does as an H plus grabber. So that's an acidic buffer. Ammonium ion. I purposely pick ammonium ion because, interestingly enough, nature has dictated that Ka ammonium ion, 5.6 times 10 to minus 6, is numerically equivalent to Kb acetate ion. And Kb ammonia, 1.8 times 10 to minus 5, is numerically equivalent to Ka acetic acid. So at least in wrestling with the ammonium ion buffer, if you've looked at the discussion of the acetic acid acetate ion buffer in the note, you'll see similar numbers, with again the intention being on my part that you focus on the chemistry and not get bewildered by the numbers. Hydronium ion concentration for the ammonium ion buffer, discussed in question 38, winds up being this to 3 sig figs, for which the pH is this. Now we go to question 39. What question 39 asks you to do is to consider treating this ammonium ion buffer with HCl gas with the intention of quadrupling the hydronium ion concentration that's present in the ammonium ion buffer from question 38. Well, there's that hydronium ion concentration. If I quadruple it, I get this. Nothing fancy about that. Now then, to pursue calculation of the amount of HCl that you must add to bring about this change in hydronium ion concentration requires use of Ka ammonium ion, or what else? Beside Ka ammonium ion, what equilibrium expression could you employ to calculate the amount of HCl to be added?
Kb ammonia?
Yeah, of course. The two principal species in this solution which dictate resulting solution pH, ammonium ion and its conjugate base ammonia. You can use Ka or Kb, doesn't matter. They both apply. I used Ka, who cares? Here's the chemistry. If you quantitatively inventory the ammonium ion buffer system with that hydronium ion molarity of 1.12 times 10 to the minus 9, you discover that hydronium ion concentration and corresponding pH of 8.95 resulted from an ammonium ion mix with 0.12 moles of ammonium ion and 0.060 moles of ammonia. Or, as a ratio, the ammonium ion concentration is 20 times the ammonia concentration. Isn't that interesting? The acid component of this system is present at a molarity that's 20 times greater than the base component, yet the system is basic. There's nothing unreasonable about this, since, as we've already noted, Kb ammonia is a very large number compared to Ka ammonium ion. 1.8 times 10 to the minus 5 is a hell of a lot bigger than 5.6 times 10 to the minus 10. Now, when you add the HCl gas to this system, here's the reaction that occurs. For reasons I don't understand, when students get to this, oftentimes they forget all this PSI stuff we talked about, and they take the HCl reacted with water, make hydronium ion, and then hydronium ion reaches over to ammonia and reacts. No! That added HCl is going to get in there with the strongest base present in appreciable concentration. And in this solution, that's ammonia, not water. 100% for this reaction? Hell, if HCl can react with water 100% extent, which we already know to be true, it surely reacts with ammonia to 100% extent, because ammonia is a much stronger H plus grabber than water. Always we emphasize the chemistry. Then you can understand what's going on and do the corresponding arithmetic correctly. But if you forget the chemistry, you are lost. You have no chance. There are no recipes in which you can shove this data and then push the right buttons on the calculator to get the solution. That's why I don't give a damn what kind of calculator you folks use. Students often ask me, what kind of calculator? Yeah, you don't give a damn. You bring in an IBM mainframe. I don't care. I don't care if you're access to every computer in the world. I don't care. I don't care. Because what I'm after is understanding chemistry. And when you can find the computer that can deal with this stuff, then you'll have a real marvelous machine. So here's what results. Ka ammonium ion. The resulting hydronium ion concentration is this, as we demonstrated there. The ammonium molarity is reduced by the amount of HCl added, represented as X. So the ammonia moles would become 0.060 minus X. And now you might ask, An equilibrium constant expression calls for concentrations, doesn't it? Do I have to convert that to concentration to do this arithmetic? Hell no! Why should I take this mole amount and divide it by the solution volume, and then go to the denominator and take this mole amount and divide it by the same solution volume? That doesn't change anything arithmetically. Don't do arithmetic you don't have to do. Always keep this computer active. Always think. Never blindly shove data into a recipe or a formula or an equilibrium constant. Don't do that. So you do the arithmetic, and here's how much HCl has to be added. Just to reinforce understanding of this, question 40 is really along the same theme. Question 40 says, which you know because you've got this in the notes. Let's take a 100 milliliter volume of 0.10 molar acetic acid solution and treat it with sodium hydroxide solution. The sodium hydroxide solution molarity is 0.10. With the intention of creating an acetate ion acetic acid buffer, which buffers at pH 5.00. Right? That's the question. Now, first we recognize that in 100 milliliters of 0.10 molar acetic acid, you have specifically 0.010 moles of acetic acid. Okay? Because when you write reaction equations, this is a mole relationship, not a concentration relationship. So whenever, as we've already noted, you have to quantitatively consider principal species inventory, it's moles that you have to get at. What does the hydroxide ion added from the sodium hydroxide solution do? It clobbers acetic acid molecules and turns them into acetate ion. So all that X in this case represent the added hydroxide ion. That murders some of the acetic acid, which initially is 0.010, less X the amount murdered. And the amount murdered is equal to the acetate ion produced. Okay? And what we want to know is, how many moles of acetate ion, how many moles of hydroxide ion did we have to add to produce this acetate ion molarity? Which, along with acetic acid, gives us a solution that buffers at pH 5.00. What's the hydronium ion concentration at pH 5.00? What is the hydronium ion concentration at pH 5.00? It's 1.0 times 10 to minus 5. Does this look familiar? Ooh, yeah. You see this? Where'd this come from? Is this magic? Nothing magic about this. Does this look familiar? I sure as hell hope so. So I'm going to take this and rearrange it ever so slightly so as to write this as a ratio of acetate ion molarity to acetic acid molarity. That means, watch out for this real fancy algebra move. I'm going to grab this hydronium ion concentration and I'm going to put it here. That's what I did. See? And then I got an acetate ion molarity, acetic acid molarity ratio. Because this ratio tells me if the pH is 5.00, the hydronium ion concentration is 1.0 times 10 to the minus 5, which tells me I'm trying to make an acetic acid acetate ion buffer in which the mole ratio of acetate ion to acetic acid is this, 1.8 to 1. Now I got a handle on how much hydroxide ion to add. It is. Get that stuff out of the way. So, I recognize, as we've already noted, moles of hydroxide ion added is represented by X, which is equal to moles of acetate ion created by this reaction. Okay? And from this, right here, I write an equation. Because this tells me right here that in this resulting solution, the acetate ion molarity is equal to 1.8 times the acetic acid molarity. And since these are in the same solution, I again don't give a damn about volume. I'll go straight to moles. So, I write X, which is moles of acetate ion, which is moles of hydroxide ion added, is 1.8 times the equilibrium quantity of acetic acid, which is 0.010 less X. Solve it for X, big deal. 0.0064 moles of hydroxide ion. Now the question goes on to say, if I'm supplying this hydroxide ion with 10th molar sodium hydroxide solution, what volume of sodium hydroxide solution must I add? There's nothing to that, provided you keep in mind the dimensions for molarity. That's all it is. Here's the inverted molarity of the sodium hydroxide solution. Why did I invert the molarity? What did this question say calculate? Volume of sodium hydroxide solution. If you let the units talk to you, you can always do dimensional analysis successfully. And if you don't let the units talk to you, you will be forever lost in science class when it comes to the requirement of writing a setup. You have to let the units talk to you. You have to let the question tell you, what units are you trying to get? And I'm going to tell you, like it or not, the textbooks got this all fouled up. They don't know how to do dimensional analysis worth a squat. And you wonder why I kick these damn dumb books out the door. They interfere with the educational process. I don't want that stuff in here. There it is, 64 milliliters. So we go to question 41. Now, for question 41, I'm going to write here, recall question 1822. If you look back in the notes at question 1822, you'll recognize how question 1841 relates to question 1822. Question 1822 is about mixing sodium sulfide solution with hydrochloric acid solution. And in so doing, putting together, combining equal mole quantities of hydroxide ion and hydronium ion. And we talked you through what you have to consider to solve that. We said, don't stop to reach the false conclusion that because you mixed equal moles of hydronium ion and hydroxide ion, that solution will result in a pH of 7.00 and be neutral. Because hydrogen sulfide ion is also in there as part and parcel of the sodium sulfide solution. And hydrogen sulfide ion, as our acid-base table tells us, has the capacity to behave as a Bronsted base in water solution because it's a stronger Bronsted base than water. So we know the solution is going to be basic before we do any calculation. And the pH for that solution was given in question 1822. I wasn't thinking it was 9.74. I don't know. Who cares? But to go on with that, you use Kb for hydrogen sulfide ion. And now you have a single solute system, HS minus, so you can use the X squared over M sub I minus X recipe. And you got to calculate the initial molarity of HS minus. Well, you found out from the mixtures made how many moles of that stuff you got. And you know the total solution volume. So you get the molarity. Then you apply x squared over m sub I minus x. So that's the reference back to question 1822. Now what we're going to do is for question 1841, start with our QPSI. $300 milliliters. I'm now reading question 1841. You got it in the notes. 300 milliliters of 0.050 molar HCl, for which the QPSI is 0.015 moles of hydronium ion and 0.015 moles of chloride ion, and I'll even line this out. We don't give a damn about chloride ion in the system from an acid-base standpoint, because it's a a base weaker than water. It's interesting how I synthesized base and weaker and came up with beaker. It's a hybrid. And the other solution is containing 0.01 moles hydroxide ion and 0.010 moles of HS minus. This again is a sodium sulfide solution. 10th molar, 100 milliliters. 10th molar to 2 sig figs. That's in the statement of the question, which you all have. All right? So when we bring these two solutions together, the HCl solution with this QPSI, with the sodium sulfide solution with this QPSI, we go back and play the game that we learned how to play way back when. We look at this QPSI and we pick out the strongest acid, that's hydronium ion. And the strongest base, that's hydroxide ion. And write a reaction equation which shows them combining, giving a reaction which we know is exceptionally large extent because it's got a K value of 1 times 10 to the 14th, because it corresponds to 1 over KW. And realize that when we made this mix, which species, hydronium ion or hydroxide ion, gets mopped up totally? Hydroxide. And what's left? 0.0050 moles of hydronium ion. Is there anything in this pot with which hydronium ion will react effectively? Yes. What is that species? Water. What is that species? HS. It is? It's HS minus. Oh yeah, hydronium ion reacts with water, but that leads to no net change in system. Just playing the game like we've learned how to play. So we write also this reaction equation. Oh, no, that's okay. Extent? Large. You betcha. And now at this juncture, if you pay attention to the mole quantities we have listed in our QPSI, and think about the chemistry of these two reactions, you'll realize now have 0.0050 moles each of what? Of what species, which will dictate pH for this solution? Remember, after the first reaction, we had 0.0050 moles of hydronium ion? Well, that wiped out 0.0050 moles of HS minus. I got all kinds of students when I do this say, oh, you kill all the HS minus. I said, like hell you do. You can't do that. If gumdrops cost $1 a pound and you only got 50 cents, damn it, you ain't going to buy a pound of them gumdrops. Unless the candy store guy is goofy. Consequently, when we put the 0.0050 moles of hydronium ion with the 0.010 moles of HS minus, we mopped up half the HS minus and converted it to H2S. So guess what we now have? Tell me in your own words, what do we now have? We have an H2S HS minus buffer. And a very interesting H2S HS minus buffer, because in this H2S HS minus buffer, how do the molarities of H2S and HS minus compare? They are equal. So if I write, for example, Ka for H2S. I could also write Kb for HS minus. Who cares? Well, if I got a question that's asking me for hydronium ion or pH, I usually go for Ka, because that immediately pinpoints hydronium ion. And if I'm looking for PHO, negative log to the base 10 of the hydroxide ion molarity, if I'm looking for calculating the concentration of conjugate base, then I'm going to go with Kb. I'm going to use the equilibrium constant ratio, which gets directly at the quantity I'm supposed to calculate. Ha ha! Boy, this is tough. There's the hydronium ion concentration. 1.1 times 10 to the minus 7. You see, we did the important part. That's the chemistry. The arithmetic is always a piece of cake if you do and understand the chemistry. And if you don't understand the chemistry, I don't give a damn what arithmetic you do, you're not going to get any place with it. It will do nothing but give you a headache. And run around babbling, I hate chemistry, blah, 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 blah. I don't want that. And without any fancy thought, I now know that I have a solution for which the pH compares how to 7.00? Compares how to 7.00? Very close? You're damn right. Isn't this about 1.0 times 10 to the minus 7? But it's a little bit bigger than 1.0 times 10 to the minus 7. So I know the solution pH is a little bit less than 7.00. That's what you always want to think about. What is the chemistry of this system? And then the arithmetic follows. What does it come to be? I think it's 6.96. I don't know. I don't give a damn. We've done the important part. Yeah. All right? Now I'm going to have to post some stuff about questions 42 and 43. No big deal. Directive, don't pick up stuff yet. We're going to tackle a little bit of 42. You see question 35 here? Keep this in mind because question 43 relates directly to this question. This one. Now then, question 42. Let me tell you what's going on chemistry-wise in question 42. Because that's the important part, the chemistry part. We are going to consider 5.0 milliliters of deionized water, as well as 5.0 milliliters of 0.50 molar acetic acid solution. In the first experiment, we're going to treat this 5.0 milliliter volume of deionized water with 5 drops. I believe it's 5 drops. Let me be sure. Yep, 5 drops of 0.50 molar HCl. Question from 2045. Do you remember the approximate volume of aqueous liquid, 1 drop? Good. .050 mils equals V drop of aqueous liquid. Now I'm cheating a little bit here, but since I want this calculation done in 2 sig figs, I will carry on with cheating. If I want to cheat, I'll cheat. And you can cheat too, if I give you permission. You think this is important, useful information? In 46L, by now I think you've realized, oftentimes you have to deal with small quantities of solutions. Well, hell, if you want a 0.5 milliliter of some reagent that's on the side shelf, you want to go take this 10 mil graduated cylinder and fiddle around with it and clean it and then try to get that last water out of there and pour in it. You got the 0.5 mil and then you got to dump it out, and then you see some of the stuff stayed in there because water solutions and glass stick to each other electrically, and then you got to rinse that out. To hell with that. Get out your dropper and count 10 drops. 1, 2, 3, 4, 5, 6, 7, 8. There's your 0.5 mil all done. I mean, that's nothing to it. If you think, here's what we're going to do. Experiment 1. 5 drops, 0.5 molar HCl to this solution. That's going to give us a hydronium ion concentration of 0.024 molar, because all you're really doing is diluting this. So what do you have to do? You got to figure out how many moles of hydronium ion you got here, and take that total moles of hydronium ion and divide it by the solution volume. You can get the solution volume from this. And that's from where you'll get this. And then you're going to take the 5 mils of the 0.5 molar acetic acid and treat it with the same quantity of 0.5 molar HCl. And here's the question. Hydronium ion concentration for the acetic acid solution after it's been treated with the HCl. Will it be this value? Or will it be a value that's greater than this, because in the acetic acid solution we have this equilibrium alive and well. Right? That's alive and well in acetic acid solution. In this acetic acid solution, will the ionization of acetic acid contribute measurably to the resulting hydronium ion concentration? Because if it does, the hydronium ion concentration for the HAC treated solution is going to be greater than this number. But you think it's possible that by adding this external source of hydronium ion, that we will have suppressed the ability of HAC to react with water, to the extent that this ionization reaction will not contribute to the resulting hydronium ion concentration? Because if the HAC's ionization ability is suppressed to that extent, the hydronium ion concentration for the HAC treated solution is this. And that's exactly what we're going to find out. So I've already told you the problem. Now we're going to do the calculation to verify that. All right? And I'll show you this stuff on Sakai. It'll be there soon, so that you can take a look at this, just so we can wrap up this buffer stuff.